I think in the end, what we all need is to embrace the chaos.
Woo!
You and I just yelling off the balcony, late July, just waiting for your friends to leave. And finally, so can we, so can we.
What?
In the back of the car, trying to stay awake. I can tell from the stars that we're out of LA. With your hand hanging out the window like you're riding on a wave. I'm no good at goodbyes, but always running away.
There's been some requests that actually I take a couple minutes to just answer some questions from some fans, and so printed off some of these great comments that I've posted, and I just want to share them with you and see if I can address some of the things that you guys have been asking about. So the first one comes from Van Dyke Rules 84. Why do you always wear the exact same thing in your videos? Well, it's not really much of a, I mean, it's not like the undershirt's clean. Like today I have a green shirt on. Okay, so like it's total like okay. Back to the content questions. All right. Okay, next one is from PVD Bio. Sounds okay. Are you aware that no one's watching your videos? Well, that cannot be true, because if no one's watching, then how do you have time to actually post these comments? So clearly you're actually watching these videos. Next question.
Know what it is, but I feel good about it.
This is not okay. All right. This one's from Phil. It's Phil. Are you purposely making? Sorry, let me read that again. Why is your intro to your video actually longer than your content? Do you feel like the students are actually learning anything? Okay, listen. I don't know. Let's just do one more question. Okay, the last one, it says it's from Philip Not Bill 84. Oh, Van Dyke, I cannot believe you wrote. Okay, where do you get your inspiration from for your videos? Oh, nice, a good question. Most of my inspiration comes from no, I read the whole question. Like that's what it said. Where do you get your inspiration from your videos? Oh. Because they're awful and you should stop with every... Okay, I don't know whose idea it was to have this video thing where we would comment on each other's stuff, but this is a terrible idea. Can we...
I'm looking at you, laughing, screaming. Head out the window, I love you, I mean it. I don't know what it is, but I feel good about it.
So, what would you little maniacs like to do first?
Watching through our fingers, watching through our fingers.
Shuts my eyes and count to 10. It goes in one ear out the other, one ear out the other. Burning bright right till the end. Now you'll be missing from the photographs, missing from the photographs.
Chemistry is a lot like cooking. Wait. No, never mind. Actually, it's nothing like cooking. It's completely different. Honestly, it's not. I mean, it's probably more like this, but I don't know what this is. So, chemistry is a lot like cooking. All right. Honestly, like, what am I trying to do here? Talking about cooking. Most of you guys probably don't even know how to cook at all. You're just staring at a computer screen saying, "When does he need it to the point?" Like, what is this even about? What are we trying to do here? Uh, well, okay. We'll get there. So chemistry really is sort of a beautiful thing, but it's not so much as cooking as it is change. And what we see in the natural world and taking place, we can witness on our own shelf looking at our various chemical reactions taking place. Now, our goal is to try and quantify these reactions, to try and notice the before, the change, and the after as we look through what's known as the BCA chart. But for some reason, when chemistry talks about change, they constantly talk about sandwiches. Honest to goodness, sandwiches. There's entire websites dedicated to it. For example, the one I posted on Classroom today. You can play with sandwiches and, make a cheese sandwich, for example. But it's a terrible sandwich, so let's go meat and cheese. All right, okay. So 2 pieces of bread, 1 piece of meat, cheese sandwich. Okay, so 2 bread, 1 meat, cheese. Sandwich. No leftovers. I need more cheese. Yeah, that's good. That's good. More meat, sweet. Oh, ooh, we just got a bunch of leftovers. Made some more sandwiches. Makes perfect sense. But this is still a weird sandwich. No, let's go with the custom sandwich. Okay, because let's do it. This kid's 3 pieces of bread. Okay, 2, 3. Yeah, this thing maxes out at 3. What are we doing here? Okay, so my 3-piece of bread sandwich here. I had some meat, spam in some cheese there, and I got some weird sandwiches and a whole bunch of leftovers. And leftovers are really our problem. So when we look at a molecular scale and start adding in hydrogens and oxygens and hoping for the best, you can see that we can end up with leftovers on a molecular scale. Well, let's see how good we are. Level 3. I can do. Yeah, I got this. Oop! I immediately regret my decision. Okay, so what is this saying? Reactants, products, leftovers. Okay, let's see. All right, so just throw some hydrogens, 3 and 1 carbon monoxide. Let's check that. Ooh, not good. Okay, so that's wrong. All right, let's double check. There must be some leftovers. So it's a 1-to-1, 1 methane and 1 water makes 3 of those. And oh wait, there's another methane and some more water. So, okay, so we're gonna make 3 more hydrogens and 1 more carbon monoxide, and then I got some leftovers. So 1, 2, 3, 4, 5 waters left over. 1, 2, 3, 4, 5, and check. Nailed it.
When it's tough, when you get stuck, you hit the wall of the writer's block. You need a spark, a light in the dark, she'll get you out of your head and into your heart.
So how does this actually look for us in our classroom? So before we do anything with this problem, we should probably go ahead and balance it to keep track of how many pieces we need for everything on there. There we go. That's better. And now we can see that for every 1 C2H4, 3 oxygens are going to interact to create 2 carbon dioxides and 2 waters. This is going to be really important for us because it's like our pieces of our sandwich. How many are interacting with one another to help make those products? So before we can try and figure out how many have been used up or changed or left over or made, we need to start with what the problem gives us. The 2.7 moles of the C2H4 and the 6.3 moles of the O2. Remember, of course, in chemistry, we're not making sandwiches, we're making molecules. So our quantity is based entirely off of the mole. Don't let that bother you right now as you first look at this. All we're going to do is drag down that balanced equation and then write in the before, or in other words, our starting value pieces. And this is the part that is actually unique and sort of brand new to us here, is talking about as the reaction proceeds, what will happen. And our x value here is going to actually represent the total number of reactions taking place given these starting values. But for us, let's just call it how many times it actually makes a product, or how many times you were to make a sandwich before. We don't really know, we just know our starting values, and we know that it's going to cycle. For example, every single time that this reaction proceeds, however many cycles it goes through, 1 C2H4 will be used up, and that's why it'll be subtracted in the minus x. But in that process, 3 O2s will be used up, which is why 3 times that cycled value is being subtracted from the beginning substances. On the product side, however, you have a coefficient of 2 for both of your products. And that means that through 1 cycle, however many that may be, we will add 2 for our first product and 2 for our second product. Now the x here again is just representing cycles, or the total number of reactions that we're proceeding through. So now if you look at these 2 reactants, you have the first one going through 1 cycle, and the second one going through 1 cycle but being used 3 times. These reactants, one of which is going to run out and be our limiting reactant. So if we set one of them to 0, and honestly it doesn't matter which one you pick, you'll see me usually choose the first one. You could say that 2.7 moles minus X is equal to 0. That would be assuming that all of the C2H4 reacts. Now if that's the case, we can determine that X for this particular reaction is 2.7 moles. But we don't know that C2H4 is actually the one that ran out. So let's check. We go ahead and put that into the O2, which says that 6.3 moles minus 3X. Well, if X is equal to 2.7, we should have a value to tell you how much O2 is left over. So if we plug in 2.7, you'll see that 6.3 minus 3 times 2.7, well, that actually turns out to be a negative number, or negative 1.8. Now what you just determined is that you ran out of 1.8 moles extra of O2. In other words, you had 1.8 moles less than you should have to have this reaction run to completion. Either way, what you just found out was that O2 was in fact the one that ran out. The C2H4 there was plenty of. And if you wanted to, you could go ahead and set the 6.3 moles minus 3x to 0, and you'll find out that that value of x is 2.1. Well, we have 2.7 moles of C2H4. So if we need only 2.1 moles of cycles, we should have plenty of C2H4 left over, thereby saying our limiting reactant is the O2. Now here's where it gets unique, is that your limiting reactant will actually tell you how much of everything that you could possibly form. So we know 2 times the 2.1 value would be our CO2 amounts, 2 times the 2.1 value would be our H2O amounts. And so we'd find that we would produce 4.2 moles of water and 4.2 moles of carbon dioxide. We'd have no oxygen left over because it was our limiting reactant. We would have a total of 0.6 moles of C2H4 left over because 2.1 moles of it would have been used up throughout this actual reaction. And that's sort of the beauty behind using this before change after chart, is that you can see every single reactant and product formed, used through the entire process.
This one's for Elise, Norma Jean, Patty Boyd, and Carol King.
And the only thing that's truly going to make this any harder is how we get to moles. Because, of course, there are 3, maybe 4 different ways we've gone throughout the year to get to moles. But at the core of what we've been looking at is this idea of how many cycles a reaction takes place. This discussion of how we get to moles is for next week.
Every minute and every hour, I miss you, I miss you, I miss you more. Every stumble